Okay, so we're going to start chapter 2 with talking about things like percentiles and cumulative relative frequency again. We'll be looking at Z-scores and standardizing data and what will happen when we manipulate that data, and then how that will look. Since last chapter we spent a significant amount of time talking about how data looks, so now how will it look when we manipulate it a little bit. So our first description that we're going to look at here is percentile. So percentile is telling you a location within the distribution that somebody is at. Okay? It doesn't, you would never describe it as being in a percentile, but they are at a percentile. And so let's look at an example here with what we've got. We've got all these statistic scores. These two data sets here are the same. Okay? And so let's look at the stem plot. It's a little bit easier to see it because they're in order. So if we're looking at the stem plot, let's say we're going to look at a particular student. And this particular student made an 86 on this exam. So you can see their location right here, okay, at the 86. So if you look at where she stands, 21 of the students out of 25 have a lower score than her. She is student number 22. And then we've got 23, 24, and 25 at that 89, 90, and 93 above her. But 21 out of 25 observations are lower than hers. So if I figure out what that percentage is, I get that 84% of the test scores on this particular statistics test were lower than her score. What that means then is that she is at the 84th percentile. This is the same information you get when you get back like SAT scores and ACT scores. They'll tell you that you're at whatever percentile. Let's say you're at the 92nd percentile. That means 92% of the people that took the test did less than you, got lower scores than you did. You got a higher score than 92% of the population. So if this girl, the example here, her name is Jenny. So if Jenny am earning an 86, she got a higher score than 84% of the other 84% of the kids in the class. So she is at the 84th percentile. So this percentile tells her location in the distribution. Okay? If I know that I have a sample of 25 students, and I know that somebody's at the 84th percentile, okay, then I can determine that 21, I can go back and I can figure out this number. I can figure out this 21 students doing, getting a lower score than she did. So don't forget that when we talk about things like this, that you need to be able to go backward and forward. So let's look at a percentile example. So looking at the first one here, okay, so we've got, using that same data set we had before, we're looking for the percentile for the following students. So the first one here is a student named Norman, and he earned a 72 on the exam. So back looking at the stem plot, you can see that only one other student got a score that was lower than Norman's score. So again, same as before, one student got a score lower than him. There were 25 students in total, okay, which gives us a 0.04, okay, or a 4%. So to translate that then, we've got Norman scored at the 4th percentile on this particular statistics test. Okay, if we look at the next one, so now we're looking at a little girl named Katie. Okay, Katie got a score of a 93. Let's get rid of this real quick. So Katie got a score of a 93. So looking at the data again, looking at that stem plot again, her 93 is pretty high up there. Okay, she is she's the highest score. So Katie got the highest score at a 93. So with her 93, it's not a 25 out of 25. Remember, it's how many people got a score lower than her. Well, 24, because she's number 25, she's the highest. 24 out of 25 students got a score that was lower than hers. So when I put that 24 out of 25, that's going to give me 0.96. So that puts Katie at the 96th percentile. She did better than 96% of the students. Her score was the highest. So for the last one wants the percentile for the two students who earned scores of an 80. Okay, so for these two students with their score of an 80, 12 students scored lower than they did out of the 25. It doesn't matter that 2 students scored an 80. Okay? We're looking at, again, when you're looking at the stem plot there in your notes, we're looking at that 67, the 72 through the 74, the 75 through the 79. We don't care about the first 80 or anything like that. Those scores in the 60s and 70s, there are 12 of them. So 12 students got lower scores than the 2 students at the 80. So 12 out of 25 gives me my 0.48. So those 2 students are at the 48th percentile. So again, that would be their location in the distribution of this data. 48% of my data points would be lower than their score. Okay, so now let's look at a cumulative relative frequency graph. This can also show us location within the distribution. So we looked at frequency graphs before, and we looked at relative frequency graphs, relative frequencies compared to the others. So looking at this data set here, let's look at just the first few columns here. So what this data set is talking to you about is presidents and the age they were at their inauguration. Okay, so here's your age at their inauguration, and then here is the frequency. So here is how often that is happening. Okay, these were the first, this is all 44 presidents. So this is not a subset of presidents or anything. This is all 44 presidents. So we can see at ages 50 to 54, there were 13 presidents were in that age range when they were inaugurated. So we could use this first 2 columns here to make a histogram if we wanted to. And then we also looked at relative frequency when we looked at histograms. So for instance, there in the 40 to 44 range right here, 2 out of 44 presidents were in that range, so 4.5%. Again, we could make a histogram using these 2 columns if we wanted to, showing percent. Well, now let's add on something new here. Let's add in this cumulative frequency. So let's look at this 4th column here. So this cumulative frequency is how often that particular value happens, and then any value lower than that is also added into there. It's a cumulative frequency. So for instance, if I look at that 50 to 54 age range again, okay, at first there were 13, okay, not at first, there are 13 presidents that were inaugurated between that age of 50 and 54. But when I'm talking cumulative frequency, I'm adding in the 7 that were inaugurated between ages 45 and 49, and the 2 that were inaugurated between ages 40 to 44. So by the time I get to this 50 to 54 range, my cumulative frequency now is 22. And then I can also take that cumulative frequency and turn it into a cumulative relative frequency. 22 out of 44 is going to be my 50%. And by the time I get down to my highest age, down here, I'm at 100%. I've got 44 out of 44 presidents all accounted for. So to build this graph of this cumulative relative frequency, so we're building the graph of this last column right here, and so we're using the first and the last column here, and we've built this graph over here, down here on the right, this cumulative relative frequency graph. So to do this, we're going to take this value, this 4.5%, this cumulative relative frequency, and we're going to plot it at the lowest value of the next bin, of the next category. So you'll see this 4.5 is plotted right here at 45, at the lowest value of the next bin. So this 20.5 for the 45 to 49 age range, the 20.5% would be plotted at the age of 50. The 50% from the 50 to 54 age range, that would be plotted at the lowest age in the next bin, which would be 55. So there's my 50% dot there, right there at 55. And so what that tells me is that 50% of the presidents were inaugurated before they were 55 years old. Right here, it tells me that 20.5% were inaugurated before they were 50 years old. Okay, when I come up here, finally, and I get my 100, because I reach 100% at 65 to 69, so I put my 100 there at 70, so I know that 100% of presidents have been inaugurated before they were 70 years old. These cumulative relative frequency graphs are sometimes known as ogives, spelled ogives, okay? But they are sometimes known as ogives. So if you see that in a like in a question or on a free response or anything, that's what they're talking about. This ogive is the same thing as a cumulative relative frequency graph. So let's look at what we can learn from this, what we can do with this information. So let's look at these examples that use this cumulative relative frequency graph. So using the graph 2.1 on the previous page, blah, blah, blah. So let's look at part A first. Was Barack Obama, who was first inaugurated at age 47, unusually young? So what do we do with that information? Well, if we come over here to our graph, we can mark age 47, which would be about here. Okay, and if you come over on the relative frequency side, you can see that's at about 10, 11. Okay, officially it would be at 11% for the cumulative relative frequency. So let's think about what that 11% means. So what that means is that 11% of presidents were younger than him when he was inaugurated at 47. So by the at the age of 47, only 11% of presidents had been inaugurated. 89% of presidents were older than that when they were inaugurated. What this also means is that he is at, so this comes back to our percentiles, he is at, that was the worst at sign, the 11th percentile. And again, remember that means that 11% of the data points are below him. So 11% of the U.S. presidents were younger than he was when they were inaugurated, and about 89% were older. So I would say, yes, that puts him on the young end of the spectrum. So let's look at part B. So part B is asking to estimate and interpret the 65th percentile of the distribution. So let's go find our 65th percentile here. So our 65th percentile would be at the 65% for our cumulative relative frequency. So if we come over here, I'd say, what's that? Oh, that's probably a little high. Let's go down. About here, the 65 mark. So if we're at the 65th percentile, which is the same as the 65% cumulative relative frequency. This only works for cumulative. If it was just relative frequency, it wouldn't work. But remember, percentile takes all the data points below you. So when I've got cumulative relative frequency, I've been keeping track of all those data points below. So if I come down here, that 65% is about at age 50. It's supposed to be over a little bit more. Officially, it's about at age 58. Let's go with what the answer in the book says as we go through this, especially if you're following along. Okay, so that correlates there or corresponds there with age 58. So what that tells me is that what we have happening here is about 65% of all U.S. presidents were younger than age 58 when they took office. So about 65% of all presidents, because we always go this way, okay? So about 65% of all presidents were younger than age 58 when they went into office, when they were inaugurated in office. You could turn that around and say about 35% of presidents were older than 58 when they took office. But when you interpret, how it tells you here to interpret it, that interpretation is that statement, linking them both together, that about 65% of all U.S. presidents, remember our context, all U.S. presidents were younger than 58 when they were inaugurated. Again, your context, U.S. presidents, you're talking about their age of inauguration. Okay, that's the interpretation also, is when you're putting it into context. So if you think about these in terms of quartiles, if you think about where your percentile is in quartiles, okay, if you relate those two together, think about it. If somebody is at the 50th, if they're at the 50th percentile, okay, then about 50% of the data points are lower than them. Okay, so that should roughly correlate to the median. So the first quartile then should roughly correlate to the 25th percentile, and the 75th percentile should roughly correlate with the third quartile. So this should be approximately my 75th percentile, and my first quartile should be approximately my 25th percentile, with my median being about at that 50th percentile. So let's look at this multiple choice question here. Mark receives a score report detailing his performance on a statewide test. On the math section, Mark earned a raw score of 39, which placed him at the 68th percentile. This means that. So let's look at these answers here. So A here, we've got Mark did better than about 39% of the students that took the test. Well, Mark's score was a 39, but his score is not his percentile. Remember, his percentile is calculated on his score relative to everyone else's. So it's not going to be A. Score and percentile are not the same thing. So B then, Mark did worse than about 39% of the students. Again, score and percentile are not the same thing. So Mark did better than about 68% of the students that took the test. Well, again, if Mark falls at the 68th percentile here, then about 68% of the data points are lower than his. So this should be a true statement here, that Mark did better than about 68% of the students that took the test. Mark doing worse than about 68% of the students is not true. Okay, Mark did worse than about 32% of the students that took the test. Okay, and again, it doesn't matter if he got half the questions right or not. It's a percentile is relative to all the students that took the test. So let's look at this one here. Mrs. Munson is concerned about how her daughter's height and weight compare with those of other girls of the same age. She uses an online calculator to determine that her daughter is at the 87th percentile for weight. So 87th percentile for weight, and that she is at the 67th percentile for height. And you are being asked to explain to Mrs. Munson what this means. So what this would mean is if her daughter is at the 87th percentile for weight, then about 87% of girls have a lower weight than she does. Okay, as for 67th percentile, she's at the 67th percentile, so about 67% of girls are shorter than she is. Data points again to the left, so being lower than she is. And if you looked at that the other direction, then she would have about 13% of girls would have a higher weight than her, and about 33% of girls would be taller than she is. Okay, so questions 3 and 4 here refer to this cumulative relative frequency graph here on our right. The graph displays the cumulative relative frequency of the lengths of phone calls made from the mathematics department office at Gabalot High last month. So question 3 wants to know about what percent of calls lasted less than 30 minutes. So down on my x-axis here, I have my call length. So if I go find my 30 minutes here, and I go up, I hit, let's go with about 65. Okay, so about 65% of phone calls from the mathematics department at Gabalot High School lasted about 30 minutes or less, because this would incorporate all the calls there. Remember, this is my cumulative relative frequency. So going the other direction then, about 35% of calls lasted longer than 30 minutes or more from the mathematics department office at Gabalot High School last month. Again, remember all the context. We've got to use that context every single time. So number 4 asks us then to estimate the Q1 and Q3 and the IQR of the distribution. Well, our Q1 should correlate with about 25% of our data points being encompassed there. So it's probably a little high. Let's come down some. So when we go over and we follow this line down, let's say Q1 is approximately 12 minutes. And then Q3 should correlate with my about 75% of my data points. So let's come up here and come across. And then when I go down, let's go with about 32. So we're at about 32 minutes. So if we're going to calculate our IQR, we're going to take Q3 minus Q1, or 32 minutes minus 12 minutes, and we get an IQR of about 20 minutes, okay, which tells us that middle 50% of our data falls in that spread there of that ranging from 20 minutes, within a 20-minute spread, okay, is what that tells us. It tells us that middle, if we're drawing our box here, this middle 50% of data falls within this 20-minute spread here from side to side. Okay, so let's look at what we call a Z-score. So a Z-score can measure the position of the location in the data. It can measure the position as to how far away from the mean it is. If we look at our little definition there on the right, it says if X is an observation from a distribution that has a known mean and standard deviation, the standardized score for X is, and there's our formula, X minus the mean divided by the standard deviation. The standardized score is called a Z-score. So basically what you're doing, so the data we have here is for that test that we had before, okay, where we had the students in their first statistics test. And remember Jenny with her score of an 86 on the test. So what we have down here, because I wanted to be able to show you this mini tab data down here, this is one of the pieces of software that sometimes you'll see this data spit out at you. Okay, so let's kind of look at it and see what it means here. So basically this is summary statistics for us, descriptive summary statistics. But again, y'all need to be able to interpret data from printouts like this. So our first thing here, we have our N. Remember, N is sample size, so 25 tests. Okay, then it gives us mean. It gives you median. Okay, and then it gives you what's called the trimmed. We've got our trimmed mean there. Okay, our standard deviation there. Standard error of the mean, we're not there yet, so don't worry about that. Okay, then I've got minimum, maximum, my Q1, and my Q3. So it gives me my summary statistics. It gives me all that information. Okay, and so when we're standardizing her score, what we're looking at is that we know Jenny did well. Jenny was in what, the 84th percentile? So we know she did above average. Okay, the mean is an 80. We know that 21 students did worse than she did. Okay, so we know that she's above average. But the question really would be is how much above average is she? Was she just so-so? Was she, oh, the average was an 80 and you got an 81? Was she, oh, the average was an 80 and you got a 97? Okay, so how much above average was she? That's what we mean when we standardize a score. When we're our Z-score, your Z-score tells you how many standard deviations she is away from the mean. Okay, so again, it tells you how many standard deviations she is away from the mean. If she's lower, then it would be a negative. If she's above, then it would be a positive. But that's what we're doing when we're standardizing her score. Okay, we're standardizing it here. We're saying how many standard deviations away from the mean is she? Again, positive would be above. She's 2.48 standard deviations above the mean. On negative, she's negative 0.34 standard deviations below the mean. So she was really close. She almost got it. Or she was way, way above it. But that's what we're doing when we're standardizing a score. So that's what that Z-score means. Again, you've got to get the conceptual. What does it mean? Okay, it means she's this many standard deviations away from the mean. Remember, we calculate our standard deviation. That's our typical distance that a data point is away from the mean. So in this case, our mean is an 80, right? I've got a mean of an 80 here. And our standard deviation here is a 6.07. So what that means is the average score, the mean score was an 80, Okay, and a typical test score is 6.07 points above and below that 80. Okay, that would be my typical test score. That would be my that's what my standard deviation means. So then when I standardize it, I figure out how many of these standard deviations she is away from the mean. So let's look at these sample problems here. So remember we had Katie before who did a really good job. She was at the 96th percentile by scoring a 93 on the test. She had the highest score on the test. Okay, so if we want to standardize Katie's score, we want to figure out how many standard deviations away from the mean she is. We're going to calculate Katie's z-score. So her z-score is her score minus the mean, and again, we've got that data down here. So it's her score minus the mean divided by the standard deviation. And what that gives us is a 2.14. So what that means is Katie's score of a 93 is 2.14 standard deviations above the mean for the test. Katie did a really good job. She's really high up there. Okay, so let's look at Norman then. So Norman was the one that got a 72. There was only one person that got lower than he did. So Norman's z-score would be, again, his test score minus the mean, which is an 80, over the standard deviation. Well, this time we get a negative number. We get a negative 1.32. So what that means then is that Norman's score is 1.32 standard deviations below the class mean of an 80. So Norman was below average, but he wasn't as far below average as Katie was above average, okay, when we standardize those scores. So let's look at another way that we can use these z-scores. So in this example, again, we've got Jenny again. And so the day after receiving her statistics test results of an 86 from Mr. Pryor, Jenny earned an 82 on Mr. Goldstone's chemistry test. At first, she was disappointed. Then Mr. Goldstone told the class that the distribution of scores was fairly symmetric, with a mean of 76 and a standard deviation of 4. So the question here is asking on which test did Jenny perform better relative to the class and to justify our answer. So let's standardize. Again, we want to know relative to our class. So if we standardize Jenny's score on this chemistry test, if we figure out how far away from the mean she was in standard deviations for this test, we get a z-score of her on her chemistry test of a 1.50. So what that means then is that her 82 in chemistry was 1.5 standard deviations above the mean score for the class. Well, her z-score on her statistics test, okay, when that one gets standardized, she made an 86, the average was an 80, but her standard deviation was a 6.09. Her z-score is a 0.99. So what that tells us then is that relatively speaking, relative to the class, Jenny did better in chemistry, even though she got a lower score on the test. Relative to the other kids in the class, Jenny did a better job on that test because she was 1.5 standard deviations away from the mean versus only 0.99 standard deviations away from the mean in the statistics test. So we're going to stop here with z-scores. And if we don't have a chance to look at transforming data in class, then we'll watch a quick video on that one. Okay, but I think we've done enough for today.